So we have covered the first two lifetime distribution representations, and those are the survivor function and the probability density function. So we now look at the third of the lifetime distribution representations, and this is the hazard function. The hazard function, denoted by h of t, has the intuitive interpretation as the amount of risk an item is subjected to at time t. And on the next slide, we'll indicate why that risk is an appropriate term. Hazard function is a special case of the intensity function for a non-homogeneous Poisson process. The hazard function deals with one failure, whereas the non-homogeneous Poisson process deals with multiple failures. The hazard function has several aliases. It's known as the hazard rate or the failure rate, sometimes in reliability. It is known as the force of mortality or the force of decrement in actuarial science. It is known as the rate or the intensity function in point processes and extreme value theory. And finally, in vital statistics, it's known as the age-specific death rate. In economics, the reciprocal of the hazard function is known as Mills ratio. Here is the derivation of the hazard function. We begin by calculating the probability of failure between t and t plus delta t. In order to find that probability, you integrate the probability density function between t and t plus delta t. Equivalently, you can take the difference between the survivor function evaluated at t and the survivor function evaluated at t plus delta t. What we're going to do in the next step is we're going to look at that same probability, so the same event here, but now what we're going to do is condition on the fact that the item is still functioning at time t, which is another way of saying its lifetime is greater than or equal to t. This is the typical situation that you run into with conditional probability when you want the probability of one event given another event, and this will be the probability of A intersect B divided by the probability of B. So you can see that the given event here, which is the probability, probability that t is greater than or equal to t, shows up in the denominator right here. Then the numerator is the intersection of these two events right here. And if you think on a time axis about the intersection of the two, you will see that that is just the probability of failure between times t and t plus delta t. Well, immediately you can recognize the denominator as just the survivor function. If you look at the numerator is exactly what we derived up here, and we're going to substitute the difference of the survivor function at t and t plus delta t there. Now this expression depends on what you choose for delta t. For example, if the item happens to be a light bulb and you choose delta t equals 5 hours, that will give you a different conditional probability than if you choose delta t to be 10 hours. So in the next step of the derivation, what we do is we average over that interval by simply dividing the previous expression by delta t. When you do so, it becomes a rate. Finally, the last step is we take the limit as delta t approaches 0, and this will become what's known as an instantaneous failure rate. So here is the limit as delta t goes to 0, and we've got that expression above there. However, if you look at this portion right here, it turns out that is nothing more than the opposite of the definition of a derivative from calculus. So that becomes minus s prime of t, and then of course the s of t just gets transferred over right here. Well, negative s prime of t, we've seen that before, that's the density function. So in the end, we get the hazard function being the ratio of the density to the survivor function. Now the last question to be answered in the derivation here is, why is this referred to as risk? Well, if you go back to this conditional probability that we had, given we have an item that has survived to time t, if its probability of failure in the next instant is small, then its risk of failure is small. However, if this probability of failure in the next instant is high, then its risk is high. So when you see this interpreted as risk, think of it as the probability of failure in the next instant being higher or lower depending on the height of the hazard function. And once again, we are looking at positive random variable t, so this is good for t greater than or equal to 0. So similar to the interpretation for the probability density function, here is the same thing. Before we had f of t times delta t, now we have h of t times delta t, and the only difference between the probability density function and the hazard function is now you have this condition out here at the end. All hazard functions conform to two existence conditions, and the two existence conditions are they integrate to infinity and they are non-negative for all t greater than or equal to 0. Quick warning here is that you want to differentiate between the hazard function for a population and the hazard function for an individual item. So if you looked at the hazard function for, let's say, the lifetimes of people in a particular country, say the United States, then what would happen is you would consider all of the people in the United States and you'd have one hazard function. But that doesn't mean that an individual in the United States has that same hazard function. Their hazard function might be higher or lower depending on whether or not they have particular genetic background, depending on their occupation, etc. So keep in mind that there is a difference between the population and individual items' hazard functions. They are not necessarily the same. Couple notes on hazards functions. First of all, the units on a hazard function are given in failures per unit time. In reliability, sometimes we run into highly reliable items, and in that case, sometimes scientific notation will save including a lot of zeros out front of a hazard function. So you might have a hazard function which is 0.00003507. Well, you could change that to 3.507 failures per million hours. A second way to tame those units to avoid all the zeros is to switch from hours to years, and that will help avoid all those zeros. Keep in mind that the intuitive interpretation of h of t is the amount of risk that the item is subjected to at time t for the reasons given in the derivation on the last slide. There are some common shapes that show up for hazard functions, and here are four of the popular shapes. One is called IFR, and that stands for increasing failure rate, which is to say that the item is wearing out over time. The second is DFR, and that stands for decreasing failure rate, and that is to say that the item is improving over time in the sense that there is less risk over time. Another one which shows up quite often in reliability is the BT shape, which stands for a bathtub-shaped hazard function. Starts high, goes low, and then increases again at the end. Finally, the last one, a little less common, is UBT, and that stands for upside-down bathtub-shaped hazard function. Equivalently, you could call it a hump-shaped hazard function. Starts low, increases, and then goes back down after that. Here's an example. Consider a Weibull distribution defined by the survivor function S of t is equal to e to the minus lambda t to the kappa. And even though the support for this distribution is t greater than or equal to 0, and that's going to be the support for almost all of them, it's still important to include that because a survivor function without a support is not meaningful. There are two parameters. The first is a positive scale parameter lambda, and then the second parameter is a positive shape parameter kappa. And the exercise here is to find the hazard function for the Weibull distribution. So first of all, the probability density function is given here. How do you get that? The probability density function is equal to the derivative of the survivor function multiplied by -1. So that's how you get the probability density function. You just differentiate the survivor function. And finally, the hazard function from the derivation is the ratio of the probability density function to the survivor function. And you can see that when you take that ratio, these two terms cancel, and you are just left with lambda kappa lambda t to the kappa minus 1 for t greater than or equal to 0. So if you take a look at this function and you think about what happens when kappa equals 1, when kappa equals 1, this function reduces just to lambda, and lambda is the failure rate. So it reduces to a constant hazard function when kappa equals 1. Second case, this will be an increasing function when kappa is greater than 1. You'll see a picture of that on the next page. And then finally, this is decreasing when kappa is less than 1. So this is why the Weibull distribution is so popular. The hazard function has 3 different shapes that it can take on, and that makes it a very flexible lifetime distribution. Here are some pictures for the Weibull distribution, and in all cases here we have the scale parameter lambda being equal to 1. But you'll notice when kappa equals 1, you get a constant hazard function. When kappa is greater than 1, you get an increasing hazard function, so this item is wearing out. And finally, when kappa is less than 1, you get a decreasing hazard function. More generically, here are some hazard function shapes which show up from time to time. And the first one is IFR, and that's where you have a hazard function which is increasing, and that typically applies to mechanical items that undergo wear or fatigue. The second case is DFR, and that stands for decreasing failure rate, and that, for example, is an item that improves with use. An example of that is software. Software has high risk of failure when it is first written, but over time, as the bugs are pulled out, for example, the risk decreases. Finally, the last one here is BT, and BT stands for bathtub. Notice that the rate starts out high, goes down, and then finally increases at the end. This BT-shaped hazard function applies to manufactured items. For example, a manufactured item has a high risk at the beginning of its lifetime. Sometimes this is called burn-in. This could be from manufacturing defects. And then it goes into a period down here, sometimes referred to as its useful life. And then finally at the end, particularly if it has mechanical items in it, it will go through wear out, so the hazard function increases at the end. Well, this also applies not only for manufactured items, it also applies to human longevity. At the beginning of the lifetime, when you have a newborn baby, there is significant risk for that baby, and so the hazard function is high. Once you get through that, what is known as infant mortality part of the lifetime, this hazard function here will bottom out at about age 6 or 7, and from that point on there is a very, very slow increase in terms of risk as the child moves into adulthood. Here's an exercise. Find the hazard function for the exponential distribution, which has probability density function f of t equals lambda e to the minus lambda t for t greater than or equal to 0. And this parameter lambda is known as a failure rate, and there is an assumption that lambda is greater than 0 in this particular case. So first of all, we start out with the survivor function, and the survivor function will be the integral of the probability density function. So we integrate lambda e to the minus lambda tau, and we use tau here as the dummy variable. D tau, we're going to integrate with respect to tau, and this integral will go from t to infinity. When you integrate that function, you get minus e to the minus lambda tau, and that will be evaluated from t to infinity. When you plug infinity into that expression, because lambda is greater than 0, you get 0. So when you plug in t, the negative is going to cancel, and you are going to wind up with e to the minus lambda t. And once again, you include the support. That is for t greater than or equal to 0. Finally, the last step is to find the hazard function. And here is the hazard function for the exponential distribution. It is the ratio of the probability density function to the survivor function. The probability density function is given in the problem. It is lambda e to the minus lambda t. And the survivor function, we just calculated that as e to the minus lambda t. The two e to the minus lambda t's cancel, and you wind up with a constant hazard function lambda for t greater than or equal to 0. And it turns out that the exponential distribution is the only continuous distribution that has a constant hazard function.